Hi, I'm Sebastian Stock from DFKI in Germany. Together with partners from LAAS in France, we have developed an AI plan for a use case with service robots and drones. In this use case, we have two robotic experiments. One with a service robot at DFKI and another one with drones at LAAS. The idea is that despite using very different kinds of robots and different robotic middlewares, they share a common technology-specific bridge, the embedded systems bridge, that is developed together at both institutes. The first experiment of the use case deals with a service robot performing tasks in the context of human-robot collaboration. The MobiPick robot consists of a Mir 100 mobile base, a UR5 arm with a two-finger gripper mounted onto it, and additionally it has an RGBD camera that is used for detecting objects and their poses. MobiPick uses ROS as a robot middleware. So a typical task that we give MobiPick is to bring an object like a multimeter inside a box to a table or to hand over a tool to a worker. The second experiment is using drones. The drone's mission is to first survey an area to localize interesting objects. Afterwards, they have to visit each object, identify it more precisely, and process it. At the same time, the battery levels need to be monitored and taken into account. The drones are using Genome as a middleware. A typical planning task for MobiPick is to bring a multimeter inside a box to table 2. So the resulting plans are sequential, as MobiPick currently cannot perform actions in parallel. However, the plans need to be optimal in such that they don't contain unnecessary actions that the robot would perform. We modeled the problem both for classical and hierarchical planners. So as planning engines, we are currently using Fast Download or Arias. If you are interested, you can try out the robot software in a gazebo simulation environment at the link down below. To coordinate the drones, the planner also needs to handle temporal constraints as well as numeric values. Therefore, Arias is a suitable planner for this. The resulting time-triggered plan contains actions for the full fleet of drones. An example of such a plan can be seen on the right. There we have two drones, and therefore the plan also contains actions that need to be executed in parallel. Therefore, we developed a plan executor that can handle such parallelism and dispatch the actions accordingly to the different drones. We have developed the embedded systems bridge as a TSB that can be used in both experiments. The ESB is a Python library that is independent from a specific robotic framework and therefore can be used in any kind of robotic applications or also on even non-robotic applications. It provides functionalities for connecting an existing system to UP, but also provides additional functionalities for executing and monitoring a plan. These functionalities and the connection to UP are shown in the figure on the right. It consists of three parts. The first part are the robot or application-specific functionalities on the left, which are specific to each robot. So these are the parts that need to be adapted for each robot, but normally those main functionalities should be already available. The system shall then be connected to the UP library on the right, and for creating and maintaining this connection, the ESB provides functions that simplify this process and to do the mapping between the actual robot actions on the left and the UP representations on the right. And finally, the third part contains additional functions for executing and monitoring a plan produced by UP. So if we compare the MobiPick and the drones integration, then only the bottom left part, which contains the specific robot action implementations and the environment representation, needs to be changed. So the main contribution of this use case is the freely available embedded systems bridge, which is its main functionalities for interfacing UP and executing and monitoring plans. It is not specific to a robotic framework or even robotic applications in general, but could be suitable for other applications as well. Furthermore, the experiment showed that for the constraints of these two applications, unified planning's functionalities and performance of the planners is sufficient. For example, if we compare the time it takes for creating a task plan for these robotic applications, then that runtime is still quite low if we compare that to the motion planner who creates the trajectory for the robot's arm. Thank you very much for your attention.